Good morning, everyone. This is the relearning for Unit 6, Mechanical Energy. You should have the relearning paper that I gave to you. On top of it should say Law of Conservation of Energy Relearning. Make sure that your name is on it, the period you have class, as well as your period for Learning Lab. That'll help me get you your reassessment correctly. We're going to start by taking a few notes. I'd like you to start by making sure that you know these really basic definitions. So first we need to know that work is when a force acts on an object and the object moves in the direction of the force. The example here, partially hidden, is the guy pushing the lawnmower, applying a force, and the lawnmower moving in the direction that he's pushing. The equation for this, though we didn't use it and we won't use it in this relearning, is work equals force times distance. Energy is an object's ability to do work. Notice that it doesn't mean that it is doing work, it's just that it could do it. So this rock above our caveman guy has potential energy. It could fall on him. It could apply a force in a specific direction. The unit that we use all the time for energy is joule. And that's something that we have to be very careful of because one of the issues you ran into on your test is recognizing what did I give you? What is the question asking? You have to find energy or are you given energy? Potential energy is stored energy. Kinetic energy is energy of motion. And I gave you the equation there as well, though we will see it again in a little bit. The bowling ball was our example of kinetic energy. Because it is in motion, it can do work on the bowling pins, applying a force in a particular direction. Another example I gave during class was a student running down the hallway. They have a lot of kinetic energy because they could run into someone else, apply a force in a specific direction, and then cause an object to move in that direction. If they ran into me, they could apply a force and move me in the direction of that force. Next, we need to know that the law of conservation of energy is that energy cannot be created or destroyed, but it changes from one form to another. The total amount of energy has to remain the same. So if we're converting energy from potential energy to kinetic energy, we're going to start with only potential as it falls. So as it falls, this gravitational potential energy is going to turn into kinetic. It's going to lose its height, and it's going to accelerate because of gravity. The total potential energy an object has at the top equals the total kinetic energy at the bottom. Now, this is making the assumption that there is no energy lost to thermal energy, which, depending on how far it falls, how much air friction there is, there may be some, but I will tell you if there is thermal energy. And then the big idea here is this total energy equals the kinetic plus potential plus thermal. As we look at thermal energy, it's the energy of an object due to the kinetic energy of its atoms and or molecules. So it's this motion of the molecule. So temperature is the measure of an object's thermal energy. Heat is thermal energy moving from an object with more thermal energy to an object with less thermal energy. So heat is just this movement of this thermal energy. And this force of friction is going to cause molecules to move faster, increasing the temperature of the object. So on your sheet, there's two boxes. I'd like you to draw these models. And in those models, I'd like you to draw the one with, and label it with less THE, less thermal energy, and more thermal energy. And you can label this one after the force of friction is applied. So again, I'm going to put those boxes back up there so you can see them. But we want to label this one with less thermal energy. There's less motion. This one has more motion, more thermal energy. And this would be after friction has been applied. The force of friction has gotten those molecules, those atoms moving. Again, at any point, if you need to pause your video, please go ahead and do that to make sure that you get all of these notes written down. Couple key things with calculations that we messed up on the test. When you're calculating potential energy, you have to be careful. What are you given? Are you given the mass in kilograms? Or are you given the weight in newtons? If you're given the mass, you need to take the mass and multiply it by 9.8 meters per second squared and multiply it by the height. Now, another thing that we messed up is that the square in this case is part of the unit. You do not square 9.8. This square here is like another number. You have to memorize the fact that this is part of the unit and you do not square 9.8. There is no square on G. You have to memorize that. You cannot forget that. What you do square is down here, and we'll get to that in a minute. If you're given weight in newtons, weight equals mass times gravity. And so if we look here, mass times gravity, well, that's weight. So you're just going to take the weight in newtons, multiply that by the height. So it's actually the same equation. We're just, we've already done one step, or we get to skip a step. Now again, with kinetic energy equals 1/2 times mass times velocity squared. And in this case, the V is squared, so you do square the velocity. Let me say that again. You do square the velocity. You square the number that is the velocity. You have to memorize that. You have to remember that you square the velocity, and you do not square the G. There is no square in the equation for potential energy. And last but not least is this energy total equals kinetic plus potential plus thermal. Generally, we did pretty well with this, with the exception of one problem that I'll show you a different version of in a minute. And that is this. If I give you an object's mass, an object's height, and an object's velocity, you cannot add them up. Those are not energies. What you have to do at that point is use them to calculate the potential energy and calculate the kinetic energy, and then you can take those two numbers and put them into your total energy equation. You cannot just add their mass, their height, and their velocity. That's not how that works. You have to only add energy. And remember from earlier, the unit for energy is joules. And so if you're not given joules, you cannot just add. If you're not given joules, you cannot just add. All right, that's the end of the notes. I'm going to switch to the doc cam here. Not really sure. So if you're not with me yet, please find your spot. I'm going to go through these first section of problems with you. So what would the kinetic energy be of an egg drop device right before it hits the ground if it has a potential energy of 3,000 joules before it falls? Okay, I'll fix this on your example, on your paper. So what are we looking at? So I want you to get into the habit, and one thing I don't do enough with you is making a picture. So right here, your little guys got your egg drop device. Here it's PE equals 3,000 joules. what the question is asking is how much, the question is saying how much kinetic energy does it have at this point, right before it hits the ground? Well, we know that as the rock falls, or the egg drop falls, excuse me, that potential is turning to kinetic because the height is decreasing as it falls, and the velocity is increasing as it falls. It's falling faster and faster. And notice in the problem, even though I did a bad job writing it, it doesn't say anything about thermal energy. So we're going to ignore that. Sometimes in physics, we get to ignore things because they're small enough that we can ignore them. And in this case, it's small enough that we can ignore it. And so if it has 3,000 joules of potential energy here, right before it hits the ground, it's not going to have any potential energy. And so it only has kinetic. So the answer to number 1 is simply 3,000 joules. All right, let's move on to number 2. Identify the following locations on the roller coaster below. So where is the potential energy the most? Well, if we look back at our equation for potential energy, mass is constant, so that's not going to change. Gravity is constant, so that's not going to change. So we need to find when is the height the highest. Well, the height is highest at B. When is it going to be the least? Well, when the height is lowest, and so that would be C. And then if there's no potential, and it doesn't talk about thermal, then all of the energy must have turned into kinetic. So the kinetic energy has to be the most when the potential energy is the least. So the kinetic energy has to be the most at C. Now we also know that fastest has to do with velocity. So when it's fastest, it's going to have the highest velocity. And when it has the highest velocity, that means that it has the highest kinetic energy. And so when the kinetic energy is the most, it's also moving the fastest. So it's also C. Now, where does it have the lowest velocity? Well, the lowest velocity would be at B, right before it falls. At this point, it probably has 0 or very little velocity right before the roller coaster starts moving. Now, one thing to make clear is this roller coaster is getting pulled up here and then it's moving this direction. So it's moving around the track like this, obviously on the top of the track, not like my arrows are. Okay, so it's moving from left to right. Moving on. If there was 100 joules of potential energy at A, how much kinetic energy would there be at D? Well, this is much like number 1 in the problems I gave you on the previous page. If it only has potential here, it basically only has kinetic there. So it's going to have 100 joules. In the same system, so that means we're going to say there's a total of total energy is going to be 100 joules here. At B, if there was 65 of potential energy and 10 joules of thermal energy, how much kinetic energy was there? So I'm going to write my equation. Notice I have all joules. So we're only dealing with joules. We don't have to do any sort of calculation to find the kinetic or the potential using our mass or height equations or anything like that. So we're going to use this equation. E total equals kinetic energy plus potential energy plus thermal energy. And I'm going to plug my numbers in. So 100 joules equals, we don't know what kinetic energy is, plus 65 joules of potential plus 10 joules of thermal. Well, I can combine and I get 75, and then I subtract 75 from both sides, and I get that our kinetic energy equals 25 joules. And to make things easier on my teacher, then make sure I go ahead and box in my answer or put a circle around it. All right, moving on to number 3. For the same system at C, so 100 joules, would you expect it to be more kinetic or potential energy and why? All right, so let's look through that. So at C, the ball is going down the hill and then it's going to roll back up the hill. So at C, is the ball closer to the top or the bottom? Well, it's kind of in the middle, but it is closer to the bottom. And so that means the height is decreased quite a bit and the speed has increased. So we're going to expect more kinetic energy because it's closer to the bottom than the top. Number 4, a ball that weighed 16 newtons was at 8 meters from the bottom of the hill. What was the energy? So we need to look at potential energy. We need to decide which of these two equations we need to use. So take a minute, think, what have you been given? Well, we're given it newtons. So we need to use energy equals weight times height because this newtons is the unit for weight. So 16 newtons times 8 meters. Now I could do this in my head, but my brain's a little slow this morning, so we're gonna hop in and use the calculator. We got 16 times 8 equals 128. Now this is energy, so remember which unit you need to use for energy. Well, you need to use joules. And put a box around that answer or circle it. At D, a different ball has a mass of 2.4 kilograms and it was moving at 1.7 meters per second. What was the ball's kinetic energy? Again, you need to show your work. One thing that we're really struggling with is if you do not show your work, you're often not going to get it correct. Kinetic energy equals 1/2 times the mass, 2.4 kilograms, times 1.7 meters per second. And that number has to get squared. So this square applies to the 1.7. Remember, you have to square velocity because it's the velocity that's being squared in the equation. It's not on the unit, it's the velocity that's being squared. And I put parentheses in here to remind myself that that square doesn't only apply to that second. I'm going to pop back my calculator open. 0.5 times 2.4 times 1.7 times 1.7. That's the easiest way for me with this calculator. And I get 3. I'm going to round it to 3.5 joules to make it easy myself. All right. Number 6, the mass of the ball was 3.4 kilograms. And at F, it was 4 meters off the ground and was moving at 1.8 meters per second. What was its total energy? Well, I see it's asking about total energy, so I need to be able to use this equation eventually. Oh. But I don't have kinetic energy and I don't have the potential energy. There is no thermal, so I'm eventually going to be able to ignore that. But I have to calculate kinetic and the potential. So it's moving at 1 point. This is the velocity, this is the height, and this is the mass. So I can calculate, I've got potential energy, mass times the acceleration of gravity times height. PE equals 3.4 kilograms times 9.8 meters per second squared times 4 meters. So I'm going to just plug those numbers in. 3.4 times 9.8 times 4 And now I get 133 joules. So going back to my equation I need to be able to use, I don't have anything yet for kinetic, so I'm going to leave that blank. I'm going to put plus 133 joules. And I could put 133.2 or 3, excuse me. I just chose not to. So either way is fine. For kinetic energy, we have 1/2 times mass times, excuse me, making up equations over here, times velocity squared. Kinetic energy equals 1/2 times 3.4 kilograms times 1.3 meters per second squared. So I'm going to go ahead, plug that in, 0.5 times 3.4 times 1.3 times 1.3, and that gives me its kinetic energy is 2.87 joules. 2.87 joules. Now, so I should probably round that to, since my other one rounded to the whole number, I'll do 3 joules until my total energy equals 136. All right, that's how we get that. So hopefully this is helpful. There's going to be some problems you have to do now after this one. That'll give you additional practice on your own. I will check those once you turn that into me, and then I will return it if you need more practice, or if you need additional practice, you can come and see me for help, or I might assign you. So hopefully this is helpful. Please let me know if you have any problems, and well, we'll take care of it. All right, have a great day. Bye.